This definite integral then, let's look at this method. What I'm going to do is go through the method with an example, and this is exactly what you'll have to do in the assignment for this particular question. It's a technique that you do, and you do exactly the same technique for your question. It's a method to follow. So let's look at how it works. First of all, let's look at why it's called a definite integral. This means to integrate, doesn't it? And how do we integrate? We use that table of standard integrals. This is an example of the first one. So what do? Add 1 to the power, divide by the new power. So that's not overcomplicated, that part of it. What makes it a definite integral is the fact that I've got some limits, they're called limits here, 1 and 2. How do I say this? I say integrate 5x squared plus 4 between the limits 1 and 2. That's a definite integral. And what it does is it works out what the area underneath that curve is. That's the curve of 5x plus 4 that I plotted an autograph, and we're going to find the area underneath that curve between the limits of 1 and 2. So I could pick any limits. I could find the area between 0 and 2, or anything I want. So to find the area under a curve, I integrate, and then I put in the values. So I'm going to go through this method now, and then that's what I want you to follow when you do this. So you're going to need to write this down on a separate piece of paper as the method, because there won't be enough room underneath this to do it. But I'll put it in here, and it will appear in the notes on the site as usual. So let's look at this integral. Here it is. First job is integrate it. Add 1 to the power, divide by the new power. Add 1 to the 5 to the x squared to get x cubed. 5 stays there, and then divide by the new power, 3. Right. Do you remember what happens when we integrate a constant, 4? What happens in that case? Well, yes, if it was time would reappear, but whatever variable we're talking about, which in this case is x, reappears. So we get 4x. We would normally add the c at this case, but we're not going to do that. And I'll show you why as we go through. So I've integrated this. I've taken each term and used that little table of standard integrals to find out what the integral is. And now I've got to put these limits in. So the convention, and this is the convention I want you to use, is to put square brackets around the answer, 5x cubed over 3 plus 4x. Square brackets and put the limits in. And you might be remembering this now from last year if you did it. What this means is I'm going to put in 2 for x. I'm going to substitute 2 for x and work out the answer. So I'm going to replace x with 2. And then I'm going to replace x with 1. And I'm going to subtract the answer where x is 1 from the answer where x equals 2. And that will give me the area under the curve. How do I do it in practice? I use, and again, this is a convention I want you to adopt, to use a curly bracket and rewrite that function, replacing x with 2. 5. And it's a good idea, good practice to actually put a bracket around like that. Plus 4 times 3. Sorry, 2. Curly bracket. What I've done is replaced x with this, so that's my x. I've just put in the value, which in this case is 2. It's a good idea to do that, certainly with more complex ones. If you have a decimal, or especially in negative numbers, you can make mistakes if you try and do steps in your head and try and work it out as you're going along. So it's good practice to literally do that. And then I'm going to subtract, and then I'm going to rewrite the function again, but this time I'm going to replace x with 1. So just put that in for me. So hopefully you got this. Now we just work it out. This equals, this one's not too difficult to do, 2 cubed, 2 2s are 4, 2 4s are 8, 5 8s are 40, so that is 40 over 3, plus 4 2s are 8. That's the first bracket, minus, what's the next bracket? Try and be a bit tidy with your curly brackets. 1 cubed is just 1, 5 over 3, plus 4. Now I might be tempted to get out my calculator and work out what that is. So what is 40 over 3 plus 8? That goes in there. What is 5 thirds plus 4? That goes in there. And then I take one answer away from the other, and that will give me the area under the curve. So just complete that for me. I could have written it as 64 over 3 and 17 over 3. Anybody see why I could do that? How many thirds are there in 8 whole ones? How many thirds in 1 whole one? How many thirds in a whole one? How many thirds in a whole one? 3. How many thirds in 8 whole ones? 24. Plus 40? 64. How many thirds in 4 whole ones? 12. Plus 5, 17. If I left it like that, what could I do now? 64 take away 17 is 54, take away 7 is 47. I think I've done that right. Thirds, is that right? 47, 57? No, that's not quite right, is it? It's 48. 64, 54. It is 47 thirds, yeah. I could have done it like that. I'm not saying do that, but, you know, it doesn't help to try and work these things through. And then, of course, as a decimal, I could work out that what that was, how many 3s are there in 47. 15.6 recurring, isn't it? 6 recurring, which is, of course, 15 and 2 thirds, which is the exact answer. Which is the exact answer. Not exactly, no, because that means recurring, doesn't it? Da, 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 da. I'll just decide when to stop. What's the exact answer? The one on the right, 2 thirds. There is value in writing it down as a fraction because that's an exact value. Calculators writing as decimals often give you have to round, don't you, because they just go on and on and on. Small point. Okay, let's look at this now. That, in theory, is the area underneath the curve. Let's look at it. I plotted it on an autograph. Here it is. That's our curve. 5x cubed, whatever it was, 5x squared plus 4. Here it is, 5x squared plus 4. I can get autograph to find the area under the curve. Let's look at it. I'll right click on it or highlight it and then right click, find area. And we'll be looking at this more closely after Christmas as part of the distinction criteria for this assignment. Now, it uses different ways to find the area. Let's look. If I use one called the Trapezium Rule, I want to start at 1, because that's where we started our area from, and finish at 2. And that it's now divided this area up into rectangles. Look, let me just do that again. It's a bit quick. I'm using the Trapezium Rule. I'm starting at 1. I'm ending at 2. And it asks me, how many divisions do I want to split this area up into? And it's on 5 at the moment. And what it's done is, Louis, what it's done is divided this up into little rectangles. Look, now think about that problem we had in the drill. This numerical method, as it's called, does exactly what we did. It splits the area up into little rectangles. Well, actually, they're called trapeziums because they're not rectangles as such. but they're almost the same as rectangles. And then it works out the area of each trapezium and gives you the area. I can put more divisions in. I can put 15 in, which is going to give me the most accurate answer. Sorry? More divisions, the more accurate the answer. And it tells me the area underneath. Look, what's the area? 15.67 according to this numerical method down here at the bottom. So it agrees with us. What integration does, and this is a point worth noting, what integration does, the method of integration, does this exactly, but it asks the question, what happens as these strips get smaller and smaller and smaller and smaller, and in the end being infinitesimally small? What does the area turn out to be? And it concludes that the rule to find that area is very straightforward, and it's in fact the rule to find the standard integral. Where is my page has gone? That table of standard integrals we had at the beginning, and that's where that table of standard integrals comes from, by finding the area and finding out what that is if those strips go to 0. So really powerful. So the numerical method gives us an approximate answer, 15.67. Integration gives us an exact answer. That is the exact answer, 15 2/3. That's the area underneath that curve. So, just to recap, you're going to get a chance to practice some very soon. Just to recap, to find a definite integral, and I know it's a definite integral because I've got the limits in, I integrate. There it is, I integrate. Square brackets around it to say I've integrated it, but I've not put the limits in yet. Here they are. And then I put the limits in. I put the 2 in first, and then I put the 1 in. I work out what the answer is if x equals 2, or if x equals 1, and I take one away from the other. Always the top limit, take away the bottom limit. And that gives me the area. So it's quite easy to do, to find the area under a curve, if you know how to integrate. And that means you need those standard integrals that we looked at the beginning.